Ladies and gentlemen, please welcome our next speaker, Jago de Vreede, presenting the topic, Lessons Learned Using Machine Learning in Java.
Good morning. Good morning. Good morning, everyone. Welcome to the second session of today. My name is Jago de Vreede. I work for a consultancy company called Open Value in the Netherlands. But this talk has nothing to do with what I do in my day-to-day job. This talk has everything to do with my son having way too much Lego. He's 9 by now, but this idea started around 3 years ago, and he has a really big box like this, with all Lego sets disassembled, or mostly disassembled in that box. But he really likes to build those sets. So a repeating task for me became figuring out Lego bricks in that big bin and trying to sort them. So I wanted to build a Lego brick sorter machine. And the first part for that is, well, recognizing which bricks are there. So I thought machine learning would be a fun way to do that. One, to learn machine learning, and two, to eventually have a sorting machine, but still building, but this part is quite done yet. So 3 years ago, I stood here at a road, a junction. I could go two ways. I could either go in the easy way, the Python way, or go into the Java way. I'm a Java developer myself. Who here develops with Java anyway? As this is not the Java conference. More than half, that's nice. Probably filled out the non-Java developers. But as a Java developer, I like Java, and well, I thought it could be done. Well, the road is on fire and is under construction, but there's a Python on the right road, so I of course took this path. 3 years ago, I didn't know anything about machine learning, so I was bombarded with a lot of terminology like loss function, gradient descent, hyperparameters, epochs, whatever. So what I'm going to do in the next 40 minutes or so is take you through the journey that I took in the last few years, and try to get you up to speed with machine learning and how to use them. So if you want to do machine learning in Python, it's quite easy. There are a lot of frameworks in Python. There's Keras, PyTorch, TensorFlow. Those are the most popular ones. But if you're going to look at Java, there aren't that many. Well, if you filter out all the frameworks that haven't been released in the last year and are free, there are some paid Java machine learning frameworks, but well, there are not many of them. So if you Googled 3 years ago for machine learning in Java, you came up with deep learning for J. That was the top result, and that's actually what I started with. But then I began looking a bit further into what kind of frameworks there are more, and I came across Elky. But Elky is a more mathematical validation framework. So you can implement your model and you can validate that yourself. I'm not really a model builder yet, and I don't want to build models. I just want to use it. I see it as a tool, not a mathematical exercise. So this was not for me. But then I came across the Deep Java library. It's actually an abstraction layer on top of more popular frameworks like TensorFlow and PyTorch. So let's compare those, because I was started out with deep learning for J, and maybe this new framework is a little bit better. So I did some benchmarks, and I run these benchmarks on a AWS machine with a nice GPU unit. And as you can see, there is a rest in peace sign for the for J library, because that was killed by the Linux subsystem, so that didn't even came to a result. But the GGL library was really a lot faster than the other one, so it was time to change frameworks for me. But what about Java versus Python then? Because if you want to do machine learning, you should do Python then, right? That's what everybody is saying. Well, I did some benchmarks there as well, and it turns out that Java is a little bit faster than Python. Not by much, but a little bit faster. As you can see, the PyTorch in for Python, that's this one, is a full second slower than the Java one, so that's not that much. But well, that's the training part. But what about using them? Then again, it's not by much, but Java is a little bit faster here as well. So what gives? why is Python not that much faster, or why are they so comparable? Well, it's actually because you're not using Python for machine learning. No, you're using Python as an API towards a C++ engine. So you're not using Python for machine learning, you're using C++. And the same engine can be used in Java as well. So we just have a different API, and this API is an abstraction for other APIs as well. So the same API can be used for PyTorch, TensorFlow, MXNet, and some others. So that's also nice, but well, we're essentially using the same engine. So that's why they are very comparable. So let's start out with a simple exercise then. You've probably already seen this, right? This is how to confuse machine learning, cookies versus dogs. Well, you could, of course, start with ChatGPT. You could ask ChatGPT and you'll get a reasonable answer. But if you switch around two of those images in that thing, you get the same answer, because ChatGPT is hardwired to give this answer to this image. So it's not actually doing image recognition here. So let's do some human learning first, because we want to know how humans learn, and we'll see if we can map that on machine learning then. I'm going to show a picture of a dog or a muffin in the center of the screen in a moment, and raise a fist if you think it's a muffin, and raise an open hand if you think it's a dog. It's quite easy. What was that? All nice hands. It was this little doggy. So, good for you. Next one. Everyone got a muffin. That's nice. So that was this muffin. Next one. A little bit faster. Are we still with us? See some doubting hands, but all are dogs. Good. It was this dog. What was that? Is it a mop with a fist, or is the thing still think it's a dog with a hand? I see 50-50 split. That's usually the reaction that I get. It was this little doggy. The problem that what you were having was that you were trained on the dog versus muffin, and now suddenly a completely different dog came up, and a completely different, well, I don't know, what was that? But I saw some people were doubting, is this or that, and that's the exact same thing that a machine learning model will also do. It was very confident in the first few pictures that it was a dog or a muffin. But with this picture you were doubting, and that was the probability that you were right. So you probably guessed, and this is also what machine learning will do if it doesn't recognize the image. It will just guess and say with a certain probability that it is that thing. Probably going to be a low probability if it was trained for this dog or muffin. So let's do this for machine learning then. Well, I'm going to take this meme as an example. So what we first need to do is split out those dogs and muffins into two categories. You have to fix that as well, because if there is only one image that is wrong in your validation set, then that's going to be an issue. So this is going to be our validation set. This is the images that we're going to validate our model against. So we're not going to show these images to the model when it's learning, just use it as a validation. So we need a lot of images to train this model. Actually, we're going to use around, well, maybe 1,000 images per category to train this model. So a good way to get images from the internet is to use Google and use the image search. Well, there's an API for that in Python. It's only a few lines, so the devil on my shoulder used Python here, because this is a lot more code than Java. But I downloaded 2,000 of the dog images and 2,000 muffin images. Great. I thought then I was done. So this is the dataset, and maybe you can spot some problems here. There are some duplicates. So that's a bit of annoying, because we don't want the machine learning model to be really fixed on a specific image. So we want as many different images as possible. So we need to clear that out. A way to do that is using a image hash. I think everybody knows what a file hash is. You can use MD5 or SHA for a file hash. But an image hash is a thing like a file hash, but it doesn't really care about resolution or sizes or compression or whatever. So you can actually compare different images against each other, and if they are quite similar, you can actually calculate how much similar those images are. So it's really good to remove all those duplicates. So again, we can use Python for this. I won't bore you with the code here because that's quite long. But I removed everything that is similar than 1%. So this was my original data set, or at least a part of it, because there were over 1,000 images here. I'm going to run that. Only this was left. So I got 86 images per category left. So that's not really a good start. So apparently there's a lot of copy pasting going around on the internet, a little bit of resizing and that kind of stuff, and using it on different sites. So Google isn't really that good for data sets. But luckily there's a different site. I think you're all familiar with Flickr. You can download images there as well. And they have a nice assortment of muffins and dogs here as well. So we can use that again with a Python API. And when we run this, we have a nice data set. I downloaded around 250 images from Flickr because they were quite big, and well, I don't want to strain that API. So we got now around 300 images per category, maybe a little bit more, a bit less. But we want to have around 1,000 images. So how can we do that? Well, quite easily actually, because you can use data augmentation. So you can take in one image. So this image is the original image, and then you can rotate the image, maybe flip it around, and those new 6 images are completely different for the machine learning model to use. So how can you use that? Well, again with Python here, but there are some Java implementations as well. But you can use the image data generator from Keras, and you can say, okay, rotate by this amount and do a random flip and that kind of stuff. So that's nice. And with it, I got around 1,500 images per category. So that's nice. It's a good way to start. So now let's start building this in Java. Well, first we're going to start with a new project, new POM. And we're going to import a bill of materials from DGL. A bill of materials is a POM file which has all the dependencies already in there. You can use that, well, you don't have to specify specific versions later on. So we're going to use a dataset, a model zoo, and a model zoo of MXNet. MXNet is a engine that we're going to use just like TensorFlow. This was the engine that was implemented the first, but nowadays PyTorch is also a good option to train with. But this is what we have. Then we're going to create a class learning, and then we're going to load our validation set. Well, we're going to load the dataset with a repository path, and we need to do some transformation because our machine learning model needs to take in inputs as a specific size. So we're going to resize our images to 224 by 224. That will be our input size for our model. And we're going to say a add transform to tensor because images are in red, green, and blue, and red, green, and blue are values between 1 and 255. Machine learning models don't like that. They really like floating point numbers between 0 and 1, and the tensor actually converts that in the 255 to a 0 to 1. So that's quite nice. And then we're going to say we want a sampling size of 8, or let's say a batch size to 8. So let's zoom into that. So batches are the number of items that are processed within a iteration of a training. So a complete training, if you go through all your data, that's called an epoch. And that epoch is cut into iterations. And within that iteration, you will send in a number of samples, and that's your batch size. And the lower your batch size is, the more diverse your model can become. So there are some studies around here. So lowering your batch size will improve your model, most likely, but it will also increase your time. So if we look at the times, if you can see with only a batch size of 1, so feeding the model 1 images at a time, it's quite slow. With 2 images, it's doing twice as fast, and it's ramping down nicely. So for me, with this small set of two things, a batch size of 8 really works well for me. But if you have a large thing that you want to train, for example, if you want to train on 1,000 Lego bricks, you probably go for a 64 batch size or maybe even higher. So with that, we have a dataset loader, and if we run this, we get a nice progress bar. Great, we're doing something. But now we need to train a model. And which model? Because there are a lot of pre-trained models already out there and predefined models. These models are tested against a image set of 1,000 images, and you can see the results here on how accurate they are and how fast they are. So I took a model that was reasonably fast and reasonably accurate, because I want to run this on a Raspberry Pi or a other low power device later on. So I need to have something that's quite fast, and also something that is also available in our framework. And I took for this the ResNet 50 model. It's quite famous for image recognition. It's quite good, so let's use that. So we need to get that model. So we need to create an instance of a model, and we're gonna say we're gonna put a block onto that model, and that block is a ResNet model, ResNet version 4. And here we're gonna say again that 224 by 224, and our shape has a 3 there, and that 3 is for the red, green, and blue. Great. And the number of layers are 50 because it's a ResNet 50 model. There is also a ResNet 125 model, or 152 model. So you can change that around. And we need to set the output size to 2 dogs and muffins. Then we're going to use that model. So we're going to use a try block for this, and we're going to add a trainer because we wanted to train that model. So we are going to set a default training configuration with a loss function. We'll get to that in a bit. And we need to evaluate on how good that model is, and we're going to evaluate on the accuracy of this model. So that's about it for the trainer. So now we want to add some metrics because we want to see how good this model is while we're training it. So we can actually track the progress during this training run. And we need to initialize this trainer again on the same shape. So red, green, and blue 224. And we call the easytrain.fit, and we'll say we're going to train for 1 epoch. So if we run this, then with the magic of video editing, we skipped ahead a lot of time, and we see 2 numbers here, a accuracy and the loss function. While training, we have an accuracy of 73% and a loss of 0.79%. So what is that? Well, the accuracy is just the number of images that it guessed correctly. So it's just good or bad, right or wrong. So if you have an accuracy of 1, that means you have the machine learning model has guessed all the images correctly. Well, the loss function is actually the distance to perfection. It includes the certainty that the model has. So for loss function, you want to have a 0 for the best result, because 0 means that there was no deviation between the expected result and the result that it predicted. So loss functions you need to get as low as possible to 0, preferably, but you're probably never going to be at 0, probably a 0.1 or 0.2, for example. But your accuracy wants to have the most one, so 100%. So if we run this a little bit further, we have now a fully trained model, and the model had an 81% accuracy with a loss function of 0.5. Great. But our validation has a accuracy of 56%. So it's 50-50, not that great. But if we run this again, we have different results. So what gives? Well, there's actually a randomizer in machine learning. So if you don't want to have randomized results, which you probably don't, you need to set a random seed. And well, I set it to 42 because why not? And that means that every time you run this model, you get the same results. So that's quite nice if you want to change a little parameter and see if that parameter actually improved your model. Because if you don't do this, you change a parameter and, well, you never know if that parameter did the improvement or just the different random seed. So we trained the model now, but we want to use the model later on, so we need to save that to disk. Well, it's actually quite easy. You just call the save function, but the model itself does not contain the labels. So the dog or muffin, those are labels, and we need to store those labels in a separate file, so they're not integrated into the model itself. So we just write that into a file, and on every line you get a nice output. Easy. So if we run this, we get our model saved and our sysnet text file, which contains our labels. So that's nice. We're done. Or at least according to the internet, because this is where most tutorials end. But we don't want to just save the model, we also want to use that model. So here comes a lot of copy pasting, because we want to do the same thing as learning, but this time as doing. Again, we need to create the model. Why, you might ask? We're just loading the model, right? But actually we're not loading the entire model, we're just loading the parameters of that model. So the model as it is defined here is the how does the model look like, and the parameters file is just, well, the filling of that scaffolding. Well, we're just going to call model.load, and well, we have our model, and then we need to do some translation here as well. With the training we did the translation at the loading of the dataset. Now we do need to do the same things again with the classification. And if we want to use this, we can just call the model.newPredictor, because we want to create a prediction, load in an image, and just call the get prediction. And we're gonna output the prediction of this muffin here. And if we run this, you will see that it's well, guess that it was a muffin with a probability of 74%. It's nice, reasonable, and got it correct. So if we run this over our entire dataset, we can create something called a confusion matrix. On the left side you can see what it's actually supposed to be classifying, and at the top what it did. So it misclassified 3 muffins as a dog, and it's misclassified 1 dog as a muffin. So let's make things better. Well, if we create more iterations or more epochs, then you can actually see that when we train a little bit further, you can see that the actual result well, improves, and then it later on dies off a bit. So actually it's better to stop while you're ahead. So at some point the model is most optimized, and everything you do to that model becomes worse. So it's nice to stop when you're at that point. So in Python there is something called a early stopping configuration. But unfortunately that was not yet available when I was playing around with this. There was an open issue at the DGL library. Luckily it contained some code to get this working. So I had a big mouth at DevOps last year, and I said I should create a pull request, and I eventually did. And this actually got merged in December last year. So if you want to use this now, you can. So that's quite nice. And how does this look like? So within the training configuration, we previously had just a evaluator, but now we need to add a training listener that's going to save the model on every epoch, because when we stop, that model is by definition worse than the model that was before that. So we need to save every iteration or every epoch of that model, so we can actually load up the best model that we trained. So that's the first part, and then we can say a add training listener for the early stopping configuration. We can say that it has a patience of at least 2, so there must be at least 2 epochs that are worse than the best one. And we can say a maximum time that it needs to train, or at least a minimum of 3 epochs, for example. And when we run this, then we get a nice list of adult models, and you can actually pick the model that gave you the best results. So that's quite nice. So why is the model getting worse then? So it's a little bit like this game. There's something called learning rate in machine learning, and it's like this game where you have to hit the green bar at the exact right moment, right? Everybody got that in a mobile game, for example. It's just like machine learning. Only thing is, machine learning only sees the thing when it's done, it only sees that green part. Well, this is the most optimal part, but the machine learning model does not know how green that green is. It just knows it's green, but could it be better or could it be worse? And actually, when you want to train that model, it's not little iterations. You want to get to that green part as fast as possible. So what you're actually going to do is, with machine learning, skip over certain parts. And if you take the same steps every time, you're going to skip over the best part. So what you want to actually do is reduce your learning rate. So first take big steps towards the green and then slow down when you do more epochs. This is a learning rate for the exponential optimizer, for example. But there are other optimizers out there as well. A lot of mathematical things go in there, but well, the Atom optimizer is the most used out there, and well, it actually gave me the best results as well. So with that, I reran the application, and at epoch 3, I believe, I came up with this model, which only got one incorrect, and that's the best I came out with this. But it was nice, good enough for me. So there's something else that you can do, and that's called transferred learning. Well, you can take, for example, that ResNet 50 model, and you can also use that as a pre-trained model. So a model has an input at the top, and then it goes through all those layers, and at the end it will decide if it is a muffin or a dog. But what you can actually do is take a pre-trained model on different things and lock the first number of layers. And in those first layers there are a lot of basic operations like edge detection and that kind of stuff. You don't know what's in there because it's machine learning, but you can estimate that the first layers is just that. And with locking that and leaving out the last 2 layers, you can actually train those last layers very fast. And well, you should end up with the same results, but I couldn't get it any further than 50%, so it was just a guesstimation, but it is something you can use if you want. And if you want to use that, well, you can actually load up a pre-trained model, and you can also use that pre-trained model if you want, with something like the criteria API of Hibernate. I don't know if you've already seen that, but you can just say, okay, I have a builder, I want to do some image classification, I want to have a image as a input and a classification as output, and it needs to be a ResNet model, a group ID, and some filters like the number of layers and the version. And when you have loaded up this model, you can actually use it as before, but you can also change that model. You can well, take around that blocks, and you have a full fine-grained control over each block and each layer that you want to do. So I won't bore you with this, but this, yeah, you can use this if you want. But there is also something for Python and Java, because a lot of data experts or machine learning experts still use Python to create their models. But we're using the same engine. So what we can actually do is use those together. So someone in Python can create a model and export that as an open model or a saved model. It's just a few lines, and when you save this model, you can actually load this model up in Java. So that's also quite nice. It's almost the same criteria API that we've seen before. Only at this point we pointed to a path on a local file system. And of course we need to add the TensorFlow engine as a dependency, because, well, we're not having that before. And we just call the load model. And we need to do a transformation towards this model. So we need to do the same transformation that we did in Python in Java as well. Luckily there are not many transformations done here, so we just need to resize to 150 by 150. And we just can call the predictor API again. And when we run this, well, if you not have set up TensorFlow before, it will actually set up TensorFlow for you, or you can point it up towards a installation of TensorFlow if you want to use that specific version. Well, with some red lines at the end, it came out with a daisy and some other flowers, so that's nice. It actually worked. What about the Lego then? Well, I want to use this for Lego, not for dogs and muffins. So what I did, I built a conveyor belt with a camera on top, and a Lego brick will pass before the camera, and there are 3 buckets at the end of the conveyor belt. One straight ahead for the things that it did not detect or were the wrong bricks, and you can actually sort out 2 different Lego sets if you want. So it will point to one box or the other box if it's well, if you want to have there. So what does this look like? A brick will pass the camera and will end up in a bucket, luckily. So I need some images for Lego bricks. There aren't any Lego brick datasets out there, unfortunately. So I wanted to generate the images for that. As you can see, it looks quite nice, right? Can work with that. So there's a rebrickable database out there, and that rebrickable database has all the Lego sets in there and all the bricks which are used in that specific sets. So that's what I use for the set extraction. And there are luckily a lot of AutoCAD files out there for every Lego brick or every piece of Lego. And you can render that with the application called LDView. Okay, but that can export to a format for POV-Ray. And POV-Ray is a ray tracing application that's run on the command line. So that's quite nice, and it's also text-based. So that's quite nice. And then we can generate our images. So what does it look like? Well, first I generated a lot of images in all kind of different directions. And then I need to find out where the edge was. Put square on that and crop that out. But here I came across a question. To zoom in or not to zoom? Because I could crop out that specific brick, so the machine learning model was fed the most brick as possible, but I could also use the distance from the brick and try to simulate the actual camera and feed it in the entire image. So the machine learning model has more information about how big the brick is. Who thinks zooming in would be better? Who thinks the other one? That was my thought as well. Unfortunately, it's not the case. Because if you zoom in, you will give the model way more information. The model is trained to predict things. And it doesn't matter how far away from the camera that thing is, it's just a thing. And thus giving it more information on how big the thing is, by the actual size of it, it will actually give worse results. Because the image size is only 224 by 224. That's not much pixels to go on. And if you have a small Lego brick or a small Lego piece, it's quite small to begin with. And when you convert that to 224 pixels, you would end up with an image which contains the actual brick of 2 or 3 pixels. It doesn't really know what to do with it. So zooming in gave me an accuracy of 80%. While the real size gave me 65%. So zooming in it will be. Well, we're gonna create a new model for this and actually gonna take the learning class that we used before and just change the output size from 2 to 100, for example, and run it. So I created a lot of Lego bricks, but I came to the conclusion that there wasn't any progress anymore. So what I did here was for 10 pieces, I created a graph on how far on which epoch the best results would come in. Because training for 100 bricks cost me around 9 hours for a epoch. So 10 bricks is a lot more easy to work with. So scale down, because it will scale up quite nicely. So if you got the results for 10 bricks, you probably get the same results for 100 bricks, only it's going to take 10 times as longer. So as you can see, quite nice results, but I took some pictures of my phone with some real Lego bricks and I plotted that into the graph. It were only 3 bricks, but it stayed around 33%. So what gives? Well, again, a confusion matrix here will help. And what you can actually see, that it was just predicting one specific brick. So we got a 33% right. It would switch between the 301 and 3002, but it will still just predict one brick. So that wasn't really good. But that was on the epoch 17. Moving a bit further, on epoch 47, it would actually started to recognize different bricks, or at least try to mix and match different things. But it would never ever predict the 3004 brick. So a little bit of panic came to mind. So looking at the generated images and the real images, you can probably see which images are generated and which one are the real images, right? The top ones are the generated ones, and especially the smaller bricks have jagged edges, for example, because the resolution wasn't that great to start with. So I needed to improve this. So I created a new validation set, and that validation set was really taken from that specific camera on that specific height, and well, I just took some video and extracted those frames. And I baselined my previous model. So I got 5 actual bricks out for this. So the percentage came up to 20%. So that's that was what I expected. So I needed to increase the resolution because those jagged edges were just artifacts of being zoomed in too much. So that increased my model to 25%. It's a little bit better, but not that great. So given the model color information, I thought maybe if I reduce that color, I would eliminate 3 channels. So 3 times as less as input. So maybe the model would train 3 times as fast. Unfortunately, no. Because in those first layers, the color information was already stripped. But it reduces noise for the model. So if we want to use this grayscale image, we need to actually change 2 things. Of course, we need to change the input shape from 3 to 1. And we need to set the flag to load up the images to grayscale. Otherwise, it will just load grayscale images into a RGB image, and then it would crash. So benchmarking color versus gray, it's a little bit faster to do grayscale, but not by much, because well, in those first layers the color information is already lost. So giving it color information doesn't really help. But it did improve the accuracy of that model. So 28%. Getting better. Not there yet. So somebody came to me and said, well, maybe you need to lower your contrast, because contrast will give you lowering your contrast will actually remove those shadows from those real images. So removing those, removing or lessening the contrast of those real images got me to 31%. It's getting better. Then again, removing that contrast from the training images to get them at the same level, 1% more, not by much, but well, take anything by now. And then we could also increase our training dataset by using something called horizontal and vertical flipping. Like the data augmentation that we did before with the dog, we can actually do this every time. And that's because when we load the data, we first had the add transform and for the resize and to tensor. But actually this is done every time that image is loaded. So this is actually a pipeline. So the pipeline is executed every time. So if your image is already this size, you don't need to resize it anymore. So you can save up time there. But we can also do a random flip and horizontal and a random flip top to bottom. So every time that image is loaded, it's randomly flipped or not. So this gave me free data augmentation. So that's nice. A little bit better, but not that much. Then I wanted to incorporate real images to my dataset, because until this point the dataset was all generated images. So I reduced the total number to 750, and well, of course it decreased a little bit, but then I added the real images, and then it shot up to 97%. So that's quite nice. So I actually got a model that did some things. So running this through the real example, we see a lot of good classifications, and if you filter out all the non-correct classifications, you can see that the probability is all quite low. So if we filter out all the low probabilities and take an average between, well, we have multiple frames to work with, and we take an average of 3 or 6 frames, for example, we have a good result. So we got something working. So the key takeaways: creating the dataset is really the hardest part of everything. Machine learning is not that hard. Java can be used for machine learning. It's a little bit faster as well, so that's quite nice. Python still has the bigger ecosystem, so, well, probably for the data experts, you probably want to use that. But models in Python can be used in Java. So that's about it. If you want to play around with the code, it's on GitHub, and I know there's a typo in the benchmark, but hey, it's a repo name. And you can find the slides on the link or at the QR code. So, are there any questions? I think so. How much time have you spent on this project? Well, it was 3 years ago that I was started, but it was mostly on and off. Well, mostly off actually, because I have 4 kids, and I did this in the spare time that I had. So if I would squeeze up all the time in those 3 years, I would probably end up with maybe a month or so in the evening or in the weekends. It's not that much actually, but well, spread out across multiple times, a lot of context switches. When I actually found out that the new framework was a lot faster than the old framework, well, I had a mental dip, so not touched the code for a month or 6 or so. So it's well, not that much time, but it's mostly creating that data set. Are there any other questions? Why Maven? Why Gradle? Why Ant? It's just the thing that I use in my day-to-day job, because, well, I work at a corporation. So just what I was used to, and, well, not complex anything more than, well, just use what I was used to. Apart from seeing slightly faster, what other pros do you see of having Java versus Python in machine learning? Well, what I've actually seen in the real life, that there was some models trained with Python, and what they did was create a REST endpoint on top of that Python application that would take in an image and spit out the classifications with a REST endpoint. And that was actually being called by a Java application. So if you would use that model directly in Java, you wouldn't have the overhead of the well, the REST stuff. So that will be a quite good use case for it. And that's it.
We still have time for several questions from the audience. Raise your hand if you want to ask something.
And if not, I'm here all day, and thank you.